Hi, now I'm going to explain the next topic is conversion between flip-flops. Earlier in the previous lecture what I explained the different types of tables, truth table, characteristic table and excitation table. The characteristic table is prepared from the truth table and excitation table is made with the characteristic table or simply truth table. So now we can get this excitation table and by which we can prepare the conversion between one flip-flop to other flip-flop. So it is convenient way to convert from one flip-flop to other flip-flop, which we make the same one the available flip-flop by connecting extra circuits to get the other flip-flops. Sometimes may some some integrated circuits have one kind of flip-flops and the application circuit may need some other type of flip-flop. So by connecting the extra manipulated circuits and then we will achieve the required flip-flop. Let us see the flip-flop conversion and what are the steps which are involved in this conversion between one flip-flop to other flip-flop, which means that the procedure for converting one flip-flop to another flip-flop. So there are basically different types of steps which involves the conversion. Among those, the first one is step 1. Write the truth table of the desired flip-flop. The desired flip-flop. If you want to convert from one X flip-flop to Y flip-flop, so Y is the desired flip-flop. So the desired flip-flop truth table, you have to write it. Coming to the second step, obtain the excitation table for the given flip-flop from its truth table or characteristic table. The excitation table, as we know that, which is the relationship between the inputs of the flip-flop and the present state and next state of the flip-flop. So obtain the excitation table for the given flip-flop from its truth table. When we move to third step, in the third step, append this excitation table of the given flip-flop to the truth table of the desired flip-flop, and then appropriately to obtain the conversion table from this by by we can understanding of those two tables in making a single table, and by which we can convert the required equation from this table. This is called conversion table, and then once we know the conversion table, from that conversion table in the fourth step, simplify the expression for the inputs of the given flip-flop. Simplify the expression for the inputs of the given flip-flop so that what extra extra logic circuits or extra connections are required to get the desired flip-flop. So what makes the inputs of the given flip-flop so that we can achieve the desired flip-flop. In the fifth step, design the necessary circuit and make the connections accordingly. So by following these 5 steps to achieve the conversion between one flip-flop to other flip-flop. So let us see one by one. For example, if you take any conversion and then by following these 5 steps, we can achieve this conversion between one flip-flop to other flip-flop. Let us take JK flip-flop to SR flip-flop conversion of JK flip-flop to SR flip-flop. If you take this JK flip-flop to SR flip-flop, which one is given flip-flop and which one is a desired flip-flop? Here it is conversion of JK flip-flop to SR flip-flop. So the JK flip-flop is nothing but is a given flip-flop. And then SR flip-flop is nothing but a desired flip-flop. Desired flip-flop. According to the first step, SR flip-flop used to be designed using a JK flip-flops. Thus, we need to write the truth table of the desired flip-flop. The truth table of the desired flip-flop. We know that all the combinations of SR and then what is the present state and next state. And once we prepare the truth table for the desired flip-flop, nothing but SR flip-flop, and then we'll move to the next step. If you see this diagram, what is that? By seeing this diagram, we can say that the flip-flop are characteristic table for desired flip-flop. We know that take the S and R flip-flop truth table. S and R are the input and outputs. The truth table gives the relationship between input columns, input combination, and output. What will be the next state? So in this case, we can consider if it is the present state, this one. So this will be the next state by applying the desired required input. If you see this truth table or characteristic table, basically this I'm talking about many times truth table or characteristic table means basically the truth table gives the output description, like whether it is memory or whether it is set or reset or invalid. But in this output, I am clearly mentioned that logic values for the present state and next state. So sometimes we can call it as characteristic table. So what are the combinations? S is equal to 0, R is equal to 0. If present state is the SR flip-flop present state is 0, if we assume, then what would be the next state by applying 0, 0? The next state is 0 because we have a truth table of latch or flip-flop, SR flip-flop. When 0, 0 input of SR NAND flip-flop, the output is, the next state is equal to present state. So the Qn plus 1 is equal to Qn when S is equal to 0, 0. We know that. So S is equal to, again, if it is S0, R0, present state is 1, next state is also 1 because it satisfies this condition, which follows this condition. Next state is equal to present state, nothing but unchanged state when both inputs are 0, 0. And then next case, 0, S0, R1. What does it mean, S0, R1 in the SR flip-flop truth table? So it is simply we remember the 1 is take under R means reset the output. Whatever the present state, after applying 0, 1, the next state will be gets reset. So if it is 0, get reset to 0. If it is 1, get reset to 0. Whatever the input combination, the output must be reset. So this one is reset. And then next combination, 1, 0 combination. In the SR flip-flop truth table, 1, 0, 1, 0 means set, it is intended to change the set state in the output. So whatever the respect of present state, irrespective of whether it is 0 or 1. If it is 0, next state is get to set, nothing but set, nothing but logic 1. If it is already present state is 1, means we can also get the set output by it seems like unchanged, but it's not unchanged. Maybe it is in a stable state, but indirectly we can say that by meaning, by product, like it is in a set mode or set state. So then when we are giving 1, 1, irrespective of present state, next state, the output won't change, like invalid output. So we'll get the invalid output. So both outputs are getting the same output. So that's why we can consider it as a invalid state. So whether it is 0 or 1, the output is invalid. So these two cases invalid. This is the truth table. By taking this truth table, we can consider this the step 1. As we move to step 2, we can get the excitation table for the given flip-flop. Here in this case, given flip-flop is ZK flip-flop. Move to step 2. So when we jump into step 2, obtain the excitation table for a given flip-flop from its truth table. So we know that how can we get the excitation table, means from the truth table only. Let us see that the excitation table provides the details regarding to the inputs which must be provided to the flip-flop to obtain the definite next state from the known current state. So that's why I said already, if you have known the present state or current state and next state, then you can mention that what combinations of inputs. The excitation table provides the inputs which must be provided to the flip-flop to obtain the next state and the current state. So in order to achieve this excitation table, you might have known that present state and the next state. Truth table for the JK flip-flop, from which we can generate the excitation table. So by considering these two parallelly, and then we can make this excitation table. So what is the excitation table? We have a present state and also next state, and what are the combinations of J and K to get that present state changes. If present state 0 and state 0, what will be the combinations of J and K? And present state 0 and 1, what will be the combination of J and K? So which is from the created from truth table. If you observe the truth table, present state 0, to get this row, present state 0, next state 0, present state 0, next state 0, these two combinations of present state 0 and next state 0, okay, to obtain this present state 0, next state 0, what will be the, what would be the inputs J and K? So what would have been the inputs J and K? J0, K0, J0, 0, K0 and 1. These two cases. So by these are considered like J0, KG, J0, K0, J0, K1. These two cases, you will get the present state 0, and then after applying the input next state also, you get 0. So this can be represented by two cases J kept constant, so I am kept constant of J0, and K shifted from 0 to 1. So one case K may be 0 and some other case K may be 1. So in order to represent that two cases in a single one, by don't care. So this 0x means 0, by putting x in one case is 0, one case is another case is 1. 0, 0, 0, 1. You will get two cases. In these two cases, present state 0 and next state will also 0. And then the second row in the excitation table, 0 and 1. When we can get this 0 and 1? So 0, 1 case is, these two cases are 0 and 1 cases. So we can get the second row. And what combinations? 1, 1, 0, 1. So kept J constant 1, and 0, 1. The K changes from 0 to 1 means we can take that as a don't care. What does it mean? This 1 and x means indirectly 1 0 in one case, 1 1 in another case. So by taking constant 1 as a 1, and this don't care term can be taken as this one time 0 and another time 1. And next case, next row is 1 0 row. So we know that this 1 0 row, this one is the 1 0 row. At what combinations? This one is 0, 1, 1, 1, kept constant of k, and don't care in under j. And last case, last row is take these two for possibilities, like four possibilities 0 0 0 1 1 0 1 1. In the last case, if present state is 1, next state is also 1. What are the possibilities in the truth table? 1 1 case. There is the 1 1 case. This is the 1 1 case. So in this 1 1 case, we can take 0 1 j shifted from 0 to 1, k kept constant. So k kept constant 0 and j shifted to. So finally, if you see this excitation table, what would have been this j and k? To get the present state 0, next state 0 is simply 0 and x. 0x would be the input combination to get this 0 to 0, and 1x for 0 1 transition in the output, and x1 1 0 transition in the output, present state to next state, and x0 in the 1 1 combination. So 0x 1x x1 x0. This is the excitation table. From this excitation table, in the third step, we will achieve the conversion. In the third step, coming to the third step, append the excitation table on the left side and the given flip-flop to the truth table. Append the excitation table of the given flip-flop to the truth table of the desired flip-flop. You can take the truth table and then on the left side, and we can take the excitation table on the right side, and then appropriately you can get the conversion table from this single table. The conversion table is obtained by filling up the values of j, k inputs for the given qn plus 1 by referring to the excitation table. The conversion table is obtained by filling up the values of j and k inputs for the given qn and qn plus 1 by referring to the excitation table. If you see this conversion table, I am taking the S and R, the desired flip-flop, the truth table on left side. I am taking truth table on left side, excitation table on right side. Truth table on left side. So what are all the possibilities of in the SR flip-flop? So I am considering on the left side. Take the same table. Previously we have seen that. This one. So all this one is nothing but truth table. This box represents the truth table. Now fill the j and k inputs for the given qn and qn plus 1 by referring to the excitation table. So what will be the j and k? So we know that in the previous slide, what combinations of j and k for the qn and qn plus 1? If qn 0, qn plus 1 0, what would be the j and k? The same table applied to here. So if it is 0 0, jk flip-flop to excitation 0x, and if it is 1 1, x0, and 0 0 again 0x, and 1 1 1 0 can get x1, and 0 1 will get 1x, and 1 1 again we can take the x0. And how to get this one in the last two rows, invalid rows. So irrespective of j and k, so it is invalid. So present state is both are same, and also when input is s and r is 1 1, it is invalid case. For the invalid case, both j and k can be defined with the don't cares. So now we have prepared the conversion table. This conversion table now helps to preparing the k map to obtain the equation for the desired flip-flop inputs. So we have a JK flip-flop. What are the required input to J and what are the required input to K to get the SR flip-flops? Okay. So what are the required flip-flop? What are the required connections to J term, J input? In order to get that one, we will take the K map for J and K map for the K. To simplify the expression for the inputs of the given flip-flop. The given flip-flop is JK flip-flop. What connections, like what Boolean function, the simplified Boolean function is required to connect extra to J term and K term of the given flip-flop. Let us see now. Take this for output for J. This one, what will be the J? By considering all inputs like S input, R input, and the Qn is the output. To get the next state, Qn plus 1, what connections connections are required to provide to J term to get the SR flip flop conversion. So by providing the connections, we have to prepare the K map for the J column by considering the inputs S, R, Qn. That's why here it is. I am considering J terminal. For J terminal, I'm by considering the S input, R, Qn input. So I'm taking 3 variable K map. So the 3 variable S variable in the row wise and RQN in the column wise. We know that in the K map. By putting this the columns, J column, the Jth column, this Jth column 0 x 0 x 1 x x x. Where will be the logic 100 combination? The remaining all are some x, 2 zeros and 5 don't gets. You see this one 001, S is equal to 0, R is equal to 0, Q is equal to 1. Sorry, 100, 100 is 1. Remaining 5 don't gets and remaining 2 zeros. By placing all the J column in the 3 variable K map and make the prime implicant this one quad, and then there are no one lefts. So even though there are 2 don't cares, but we are focusing on logic ones in the boxes. So already covered in that one logic one. So what will be the resultant for this K map is for the J term, J output, like J column, J is equal to this entire row, which covers only one row and covers all columns. So cancel to each other all columns, so only cover the row. What is that row is S. So J is equal to S. And then if you take this K in the previous slide, if you take K here only, if you take the K here, in order to get that K, take the 3 variable K map, S, and RQN. Zero one 00011110 combination is for the K-map. And what are the logic one in the kth line? Combination of input S and RQN 011 logic 1 and 0001 logic 0 101 logic 0 remaining are don't cares. When we take all don't cares, where is the logic 1 here? In this one logic 1. In order to cover this one, we can make pad here. So there are no left ones. We can focus on only that quad. So what will be the output for K is equal to, it covers 2 rows and 2 columns. 2 rows cancel to each other in the S side, and the column wise we can take this one RQN. So what is the common term here? 1110, 1 is common, so nothing but R. K is equal to R, J is equal to S, and K is equal to R. So in this way we can get this logical expression for the inputs of J and K in terms of S, R, Q, N using the suitable simplified technique like K-map. Now we have we conclude with this simplified expression for J input and K input. We have a JK flip-flop. So what connections required to connect the J is nothing but directly connected to J. What connection required to K terminal of the given flip-flop K? R directly connected to K, so that we will make that entire flip-flop into SR flip-flop. Now when come to the fifth step, design the necessary circuit which makes the connection accordingly. Here neither additional circuit nor new connections are necessary. Take the JK JK to SR flip-flop. What connections to J? For example, we have a S, the J is equal to S. Sorry, it is J K, that J value is connected with the S terminal, and K value is connected with the R terminal, so that your conversion flip-flop is SR flip-flop. We have a JK flip-flop initially with the clock. It is a JK flip-flop. This available JK flip-flop connecting J terminal to S, connecting K terminal to R, you will get new SR flip-flop. This is from simply JK flip-flop to SR flip-flop conversion. Likewise, we can convert any flip-flop to any flip-flop by following these 5 steps. Once again, I am simply just note down the short form. Excitation for given flip-flop, and truth table for desired flip-flop, truth table for the desired flip-flop, and then add truth table with excitation table, and third step is conversion table, and fourth step is obtain the expression for required inputs like given flip-flop input so that we can get the required inputs, required flip-flop, and then synthesis, like rather logic diagram. These are these simple steps. By following those we can get the one flip-flop to other flip-flop. For example, JK to D flip-flop. Let us take one more conversion. We will get this. Step 1. This is the D flip-flop. Is to be designed using JK flip-flop. Very simple. What is the given flip-flop? What is the desired flip-flop? JK is the given flip-flop, and D flip-flop, desired flip-flop. Okay. So let us see the conversion step by step. Step 1. D flip-flop is to be designed using JK flip-flop. Thus write the truth table for the desired flip-flop, like D flip-flop. So we know the truth table. It gives the relationship between input and outputs. D is input by assuming that clock is high. When clock is high, D is 0. When D input is 0, the output is, when clock is high, the same D is passing through the next state, whatever the present state, 0 present state, next state 0. So D is 0. If present state is 1, so the same D is passing to the output in the next state. D is 1, present state 0, next state passing through the same 1 in the output. So after some delay, that D is passed to the Qt plus 1. So we know that the characteristic equation for this D flip-flop, the next state equation, the Qn plus 1, Q suffix n plus 1 is equal to D. Whatever the D input after some delay, unit delay, you will get the same D appear in the Qn plus 1 next step. So for step 1 is getting the truth table of a desired flip-flop, and then next step 2, obtain the excitation table for the given flip-flop, JK flip-flop from its truth table. We know that how to obtain this excitation table, okay, from the truth table. The truth table for JK flip-flop, excitation table, output versus inputs, present state, if you know present state Qn and Qn plus 1, and what would be the combination of J and K, 0x, 1x, x1, x0 for the JK flip-flop, 0x, 1x, x1, x0. This joining these two flip-flops, append the excitation table of the given flip-flop to the truth table and desired flip-flop appropriately to obtain the conversion table. Now, in the left side, truth table of desired flip-flop, excitation table for given flip-flop. Now, once appending of this table and conversion table, then get the characteristic equation, get the Boolean equation, simplified Boolean equation for J and Boolean equation for K using K-maps, and the equation for that K-map is for J and K, this is J input. For J, we can consider the D input and Qn input. D input and Qn input, only two variables are there. So that's why I'm taking two variable K-map. You will get J is equal to D and K is equal to D. So then what is the necessary synthesis diagram? From the Boolean function, we can make the D flip-flop. So what is existing flip-flop is the JK flip-flop, given flip-flop. This is the given flip-flop or available flip-flop. We have a JK flip-flop. What connections are required to get the D flip-flop? So in the previous, J must be connected to D. input. K must be connected to D bar input. Take the D is the one of the input in the D flip flop. Take the D directly to J term and take the D bar means by connecting inverter and connected to K terminal, and already clock is there, clock is existed. So that we will get the desired D flip flop. This is the desired D flip flop. So if J term is connected directly D and K is directly D bar, we can get the D flip flop. Similarly, we can connect any flip flop to any flip flop. So by following these 5 steps, we can achieve conversion from one flip flop to other flip flop. Here JK flip flop to T flip flop. Step 1, truth table for the desired flip flop, excitation table for the given flip flop, and then conversion table, and then Boolean function. J is equal to T and K is equal to T. Both are connected to T. Take the JK flip flop. Take the T flip flop T terminal directly connected to J and K. You will get the J and K. J is equal to T, K is equal to T. So that take the J and K connected to one single input T, so that you will get T flip flop. Likewise, you can connect. In the problem lecture, we will see any conversion to any conversion with the help of single table and make the one table to get the one conversion one flip flop to another flip. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.